Hi everyone, it's Lizzy from Wendy Labs. I have Woof here today. He's going to show you guys a few tricks. Woof, can you stand? Nice job. Can you give me paw? Oh, oh, oh no. Okay. Okay, Woof. Okay, Woof, stop. Can you sit? Can you sit? Lie down. Lie down. Training your robot dog is clearly not so easy. To understand why AI for robotics is hard, we've got to start with gradient descent.
In normal machine learning, gradient descent is how a model gets better. You define a goal, measure the error, then update the model and the direction that lowers that error. Step by step, the model moves downhill toward a better solution. But the problem is that the landscape is not always a clean, smooth hill. It is full of bumps, cliffs, flat regions, and valleys. Sometimes the model finds a solution that looks good nearby, but it's not actually the best solution overall. That is called a local minimum. Now, imagine that same problem inside a robot. A robotic arm with 6 degrees of freedom is not just choosing one movement. It's choosing how to move 6 different joints at the same time. Shoulder, elbow, wrist, rotation, grip, and orientation all interact with each other. And every action changes the next action. Move the wrist too early, and the gripper misses the object. Move the elbow too fast, and the object slips. Approach from the wrong angle, and the arm collides with the table. Add gravity, friction, latency, camera noise, motor limits, and imperfect sensors, and now the search space becomes massive. This is why robotics is so difficult. The robot is not just predicting an answer, it is acting in the physical world where mistakes have consequences. That is where reinforcement learning comes in. Instead of programming every movement by hand, reinforcement learning lets the robot learn through trial and error. We define the reward, pick up the cup, move the block, open the drawer, walk forward without falling, avoid collisions, finish the task efficiently. The robot tries actions, observes what happened, and slowly learns which behaviors lead to better rewards. Most of this training should happen in simulation first. You run thousands or millions of attempts in a safe virtual environment. You test different rewards, different objects, different starting positions, and different failures. Once the behavior looks good, you do not manually rewrite the robot. You package the result. That result becomes an artifact. The artifact might be a trained policy, model weights, configuration files, reward metadata, simulation settings, or a full containerized Wendy app. Once you are happy with the result, Wendy should make it easy to transport that artifact onto the robot. The policy gets bundled, versioned, deployed, and started on the real device through WendyOS and Wendy Agent. The robot can then run the trained behavior locally, talk to cameras and motors, collect logs, stream results back, and let the team compare what happened in the real world against what happened in simulation.
That's the full loop. Train in simulation, package the artifact, deploy it to the robot, observe real-world behavior, improve the policy, deploy again. Reinforcement learning is powerful because it can discover robot behaviors that are too complex to hand code. But it's hard because the world is highly dimensional, noisy, delayed, physical, and unforgiving. Wendy exists to make that loop easier, not just for building apps that see the world, but building physical AI systems that learn, move, act, and improve.